Let's wait for 5 more minutes and then we'll start. Okay, so yeah, let's start. I don't think so. A lot of people will be joining. So I expect you guys have finished assignments till week 3. What's the deadline? Let me check. Okay, sure. Week 5 is live, guys, now. Just today I submitted the assignment. So if you have started, you can look at it. So yeah, any doubts in till assignment 3? I think Shikha had a lot of doubts. Uh, so Barabasi Albert model, literally they have a book. Let me show you. Um, just a second. They literally have published a book. So in this book, this chapter 5, if you go to it, you can study about Barabasi Albert model. There are a lot of videos as well. So this is very detailed. Like I don't think so anyone else. Just let me check this one. I guess this one only. Random networks. This is the old version, I don't know. Here's not a proper book. This is what is this? This is acha, this chapter is chapter okay, chapter 5. Okay, okay. Yeah, I think this one is the one. Let me just match sections from here because I follow this tutorial, this whole thing, this website. Okay, I'm sharing the link here. Okay, so you can open it and you can study about Barbasi-Albert model. By the way, sir has also discussed it, Barbasi-Albert model in videos as well. Okay, any other doubts? I guess you don't have any doubts. Okay, I need to check what's written because I cannot make anything of it. Let me check. Which lecture is this? Lecture 2. Okay, hold on. At what time? 21, 23. Let me check in the book. What model is this? This is those any random network, random model. Yeah. Hmm. Few lines before probability of node being part of GC. GC is what is GC? Giant component. Okay. Is GC by N. Okay. Acha. Okay, you got confused. So there are two conditions. There are two conditions which you have to basically say that is let me explain the proof. Okay. Shall I explain the proof? Okay. So it says let Vi and Vj be pair of nodes in a random network. There's a random network. There are two nodes, Vi and Vj. Okay. And assume Vi is inside a giant component. Okay. Therefore, it must be connected to another node Vj, which must also be a part of giant component. I can close this video. If Vi does not belong to giant component, then this can happen due to the following reasons. First is the edge does not exist, but edge exists, and but Vj is not the part of giant component. Getting it? Let me connect my iPad because I have to explain a lot of things. Hello, Vishal. Good evening. Yeah, yeah. Please wait. I'm connecting iPad. Okay. Manjula was supposed to join. She asked to teach real social network analysis on a real world data set. Never mind. Sharing screen. Okay. So let me explain. I will be explaining from the book, and there are lectures on NPTEL. They also contain more or less similar language. So if it's something is different, just let me know. Okay, I'll clear the doubt. So, what is a giant component in a graph? A graph in itself, if it's connected, if all nodes are connected, what is a giant component? Somebody tell me. Vishal, what is a giant component? Hmm? Anyone? Shikha, what is a giant component? Can you just explain what is a giant component? Large connected component, correct. You're getting it. But how do you differentiate? Say, I have this network. It's connected almost fully. Then it's connected here. Okay, then it's connected here. So, which of these three is a giant component? Hmm? Okay, let us consider a case when we have a fully connected network. This is a fully connected network, right? What is the average degree of this network? 3. How? What is the formula for average degree? Hmm? Total edges by total nodes. Okay. Total degree by total nodes. With total edges, you mean? Total degree, the issue with total degree is degree of this, then degree of this. It will contain this edge common, na? So you cannot take degree. You have to take the total edges. So how many edges are there? One, two, three, four, five, six. Okay. Six, five, four. That is 3 by 2. That is 1.5. So there's a theorem 3.1 in the book, which says a giant component emerges in a random graph when average degree is greater than or equals to 1. So can we say that this is a giant component? Average degree is greater than 1. This book. Actually, I prefer this book. I don't watch NPTEL videos. I have watched it a long time back. So just to keep myself updated, the content is almost same. It's 100% same actually. The language might be different, but it's almost same. Okay. Whatever you are taught there is, yeah, it is a giant component. Correct. Then what's the difference? So basically, giant component is a component in a graph which is connected. Okay. Let me clear the definition. This graph can also contain nodes which are not connected. Correct? Am I right? Vishal, can you unmute yourself? I just want to have someone interacting with me. Otherwise, it feels a lot awkward. I think other people are traveling. Vishal, hello Vishal. Just keep on interacting with me, okay? So, so what happens is, what definition can you make from this? I mean, you're getting some intuition, right? If I take a fully connected network of four nodes, it is a giant component, correct? If I add one more node, it is a giant component, correct? How? 6 by 5. Six edges are there, five nodes are there, that is still, this is 1.2. If I add one more node, then it's still 6 by 6 is 1. Then if I add one more node, it is 6 by 7, that is less than 1. So now it is not a giant component. Now this connected thing is not a giant component because the number of nodes is greater than number of edges. So this is a basic definition of giant component. Okay. The giant component should contain significant fraction of vertices. Okay. But the thing is, this whole network is not a giant component if we consider it. But this still is a giant component inside this thing. Okay. So that is what we have to find out. So it might happen there are just something like this. So this has 2 by 3. 2 by 3. This graph is not connected. Okay. This is another subgraph inside this graph. This is one graph. So this is 2 by 3. This is 66% something. So 0.66. So out of these nodes, this one and this one, out of these things, which one is a giant component? This one is a giant component because here the degree is 1.5, average degree. Getting it? This is the basis. This is the basis of giant component. There can be multiple disconnected components present inside a random graph because it's growing randomly. It might be a case the components are not connected. There's a probability with a connection. So there might be a case it's not connected. So in that case, these are the two possibilities which can happen in a graph. Okay, when your average degree is greater than one, when your average degree is less than one. So when it's greater than one or equal to one, we consider a giant component. Okay. Now coming to the question, coming to the theorem part. Okay. So it says, say, let me. Say there is a giant component present in your graph. This giant component, okay, and node Vi is here, and node Vj is here. There is an edge between them, correct? Vishal, huh. Consider this node Vj1 and this one node Vj. So, and this Vj2 and this one node Vj3. Node Vj can exist at three places. Inside this giant component, connected to it, not connected to it, outside this component, connected to it. Correct? Yeah. And Vj can also exist like this. It's not connected at all. But then it becomes another node inside the graph. So we don't consider this case. Correct? Okay. So there are two conditions, two reasons that Vi, what is this? Okay, so VIR, let's assume there's a VI is in the giant component. It must be connected to another node VJ, which also must be a part of giant component. Okay, okay. So what is the possibility if VI, say VI does not belong to giant component? This can happen. This can happen how? Edge VI VJ does not exist. And if edge exists, but VJ does not belong to GC. Correct? All other scenarios, the giant component exists. So what is the case? Like, so if this edge is not existing here, this Vi and Vj are independent. Okay. So how this Vj is sorry Vi is Vj is part of this component, but how Vi is not part of this component, this giant component? Shika, condition one is Vi Vj is existing. This edge is existing. Sorry, it's not existing, but they are inside this giant component. So how come this condition makes Vi not a part of this giant component? Are you explaining, Shika? Okay. Say Vi and Vj, they are two pair of nodes. They are pair of nodes that exist in this graph, this random graph. Assume uh, assume Vi is in the giant component. Currently assume it. Therefore, it should be connected to another node Vj. Don't don't think it's connected to any other nodes. Okay. Let me clear it again. Let me draw it in another way so that you get it. Okay. So say this is a giant component. Inside this, there are 4, 5 nodes. This is connected. So say this is Vi and this is Vj. Okay, and they are connected. Okay, so Vi and Vj are a pair of nodes. Okay, Vi is in giant component, therefore it is connected to Vj. Okay, so what is the condition? So let us assume Vi does not belong to giant component. In that case, either this edge should not exist, or if this edge is existing, then Vj should lie outside this thing. This is not Vj then. Getting it? Vishal, getting it? So these two conditions are named S1 and S2. This is S, sorry, this is S1, this is S2. Now what we have to do is we have to just prove. We have to just prove and we have to get degree greater than 1 to show this thing. Okay. So now let us assume that, now let us calculate the probability. Let us assume this V is a part of this giant component. So what is the probability of this happening? Uh, okay. If Vi Vj does not exist, then Vi is not connected to GC. Vi is not, yeah, Vi and Vj are not connected, then Vi is not part of GC. Because then, if this is not connected, let us assume it's not connected to any other node. This is the only edge possible. Okay, this is the only edge possible. So if this is not this, even if this edge is not connected, then how can it be the part of GC? Because it won't be used in the formula, that edge by node thing. Getting it? Cool. So what is the probability of V belonging to GC? Say total number of nodes is n, number of nodes in GC. This is the way you were confused, right, Shikha? So this is different thing. That another formula S1 plus S2 is different thing. Okay, let me explain. So there are 10 nodes, out of which 5 nodes are a part of GC. You have 6th node. What is the probability that it will be a part of this thing? It will be 5 by 10, 50% probability. It can be outside here, it can be inside there. Correct? So that is how this formula is framed. Okay. So what is the probability that V does not belong to GC? It will be 1 minus GC by N. Correct? So that, let me name this probability as M. Okay. So for our two scenarios, probability of S1 is, what is probability of S1? Shikha, what is probability of S1? No, 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 1 minus P. What is P here? H does not exist. The probability, basically in a random network, what is a random network? Random network G is number of nodes comma P. Something like this. We are following this notation, right? Am I right? We are following this notation for this thing. Huh. So what is the this n is the probability of edge existing. So we say Vi and sorry Vi and Vj does not exist. So this is the probability, correct? Vishal, okay? You got this equation. You got this equation. Okay, so let me explain. So what is a random network? How do we define a random network? Random network has some, you basically, what you do is, a random network is defined like this. You supply, this is a function. You supply, say, you want 10 nodes in a random network, and the edge between 10 nodes should exist with a probability of 0.7. So between any two nodes, the edge will exist 70% of the times. Okay, something like this. It's basically computed in computer using computer seed, whatever seed computer is pushing. So it basically predicts the number. 70% of the time. Say it predicts 10 times edge will exist or not. Out of 10 times it says yes. Out of 10 times it's 7 times it says yes. Okay? So something like that. Yeah, it is fixed. In case of random network, it is fixed, and we can change that. That's what temporal random networks are there. Temporal random networks, after each iteration, you change the probability. Okay, we have no, these are not taught here, but they are basically very simple thing. So so a random network, basically what you do is, in a one snapshot you print whole network. So in temporal random network you do it iteratively, something like Albert Barabasi model. Okay, something like that, not exactly. This is a tough equation, I agree. This equation is, no, sorry, this whole theorem is not difficult, but it takes time to get. Yeah, that's why I'm explaining it like this, each and everything, one by one. Okay. So P is the probability of edge existing. What is the probability of edge not existing? 1 minus P, correct? Okay. So what is the probability of condition S2? Edge is existing. What is the probability of edge is existing? P. But it's not a part of giant component, which means it is M. You multiply both the things. Now, when you have two probabilities to be combined, you multiply both the things. Okay, so it is P comma M, sorry, P dot M. So what happens when you add it? We want these two conditions satisfied. 1 minus P plus P dot M. Correct? This is condition for one node. For one node. But you have n minus 1 nodes because your Vj is fixed. Your Vj is fixed. Not fixed basically. You are performing this condition on, sorry, your Vi is fixed. Your Vi is fixed. You are saying if it exists, if it's a part of GC or not. So what you do is, sorry, opposite way. Because every time you do it, you leave out one node. Okay, so ultimately you will be doing it for n minus 1 nodes, not for all nodes. Okay, so for one node it is this probability. So what happens when you do for all the nodes? You basically multiply them. So 1 minus P plus P dot M whole to the power n minus 1. So this is what the equation for n minus 1 nodes is. Getting it? This is the, so this is the probability. This is the probability of V not part of GC. But what is the probability of, what is this probability? This is also again, this is again the probability of V not part of GC. Because it satisfies these two conditions. We are basically creating two representations of same condition. One condition is simply the probabilistic. The other is satisfied by these S1 and S2. So what happens is we make M is equals to 1 minus P plus P dot M whole to the power n minus 1. Correct? Shika? So your doubt is cleared, I guess. The doubt from the previous condition which you had. But let me still explain it till the end, okay? So you apply log on both sides. Log of m is equals to n minus 1 log of 1 minus p plus p dot m. P is number of nodes, sorry, n minus 1. This is what? Diameter or degree? What is this? Let me check the notation. This is average degree. Yeah, so this equation of probability, this P is equal to average degree. You might have seen in, wait a second, where is that equation? Equation number is not given in the book, right? Let me check. Yeah, so yeah, there's an equation, equation 3.3 in book. So that says, let me explain this equation, then we will go how this is coming. So average degree is sum of degree of all nodes by number of nodes, which is equal to 2 into edges by number of nodes. 2 into what is edges? K upon n. Okay. What is K? If you go to this equation, uh, random network model equation, it's not given. Equation number is not given. Yes, it will be the same given the network you are using is same. Like for the same network, these two values will be the same. That is why we have equated them. So this is basically a holistic representation. What is the probability? This is basically probabilistic representation. And based on this representation, we are satisfying these two conditions. Then we are equating it. So if you see, like, if you go to the previous part of the videos, you will find that the mean of binomial representation is NP using the same average number of edges in the graph is n minus 1 by 2 dot p. Okay, so if you put it here, so you get d is equals to p dot n minus 1. So p is equal to d upon n minus 1. Okay, so that is what we put here. And when you solve it, you get log m is equals to n minus 1. Again, log 1 minus d upon n minus 1. This is d dot 1 minus m. You solve it like this, you will get it, okay? I'm not going into algebraic operations here. Log 1 plus x approximates to x when x tends to 0. Am I right? Vishal? This is a basic log property in uh, limits. You see it, okay? So you approximate log 1 plus x here to this condition. What you get is log m. Do we have in network x? It is there, I think. Let me check. Nos. What is name? Full name. I forget it. Erdos. Erdos. Rainy graph network x. See, it is there. You have to pass number of nodes. You have to pass p. Seed. If you set seed, say 1, 2, 3, and you run this command, run this with the same probability on different computer, you will get same graph. Okay, so you have to basically change randomness using this seed. That's what I was talking about. Okay, so once you get this graph, you will get a set of nodes and edges, and if you print it, you display it, you will see the graph. Try it. Okay, I will show you in some time. No, no, no. I said randomly. You can use seed anything. 42, 20, 1, 2, 3, 1, 2, 3, 4, 5, 6, anything. Okay, so yeah, we get ultimately this thing. This is equals to minus d 1 minus m. How's that? 1 to 1 gets cancelled. This remains minus m is plus. Okay. So ultimately, if you leave 1 minus m, then you get it. If you try solving it, you will get it. Okay. So when you remove log, you get uh, 1 minus m approximated to h. So h is equals to 1 minus e to the power minus d h. 1 is equals to d e to the power minus d h. Set h is equals to 0. You obtain d is equals to 1. I am sharing these notebooks. I'm sharing these notebooks here. You guys get this link, na? Feedback form link somewhere. Just let me show you. NPTEL. You go to this problem solving session here. You go to problem solving recording. Okay. You click here. You get this thing. Google Drive. I keep on putting links here. This script, this scribe. Okay. So I will put this today only. Oh, sorry. I'm sharing on my iPad. Wait a second. Ah, wait a second. Is it visible now? So on this NPTEL page, the course which you study, come here, problem solving session, click recording. Okay, you click here. This is the presentation folder link. In this folder, this scribes. This is the scribe of last session we had. Okay, this is the scribe of last to last session. This doesn't have a lot of things, but yeah, you will get here. I will post it here itself. Okay, let me share my screen again. Visible? Okay. So you saw this, right? This is the average degree. Average degree is equal to 1. We have proved it. Taking optimal condition. It is obviously greater than 1 because I showed you this example here. Why is it greater than 1? Why is it? Okay, this example basically does not prove anything. It just shows why a giant component generally has degree greater than 1 or equal to 1. And that this is the proof. Okay. Any other question? Anyone? 12 people are there. Anyone? Any question? Shikha, your doubt is cleared, right? Okay. So shall we discuss week 3 assignment? Or you guys want to discuss anything else? Anything coding related? You want to see how what is ADOS Lenny graph works? I can show you. Yes, on network X. Okay, I'll show. Anyone else? Any other things you want to discuss? Like we have 10 people. Actually, I'm repeated 3 times, so there are 9 people. You guys don't have to ask anything. Small to smallest doubt, coding related, anything, Python, how to print a statement, anything. Like we can discuss here. Okay, then I will show this thing. Erdos running graph. I will also show Albert Barabasi model as well. And there's also a ring lattice network. These all these four things I will show. Ring lattice network is also a bit difficult. Not difficult, I would say it's confusing. Okay. So back to coding. My screen is visible. When do we use Jiffy? When you don't want to code the visualization, then that's where we use Jiffy. So the thing is, you know coding, very good. But coding does not solve a lot of visualization issues. Okay. So what happens is you cannot create a perfect visualization with just coding. You need to observe the graph first. And with a million of nodes, billion of nodes, you cannot use coding based visualizations. Okay, you need to rotate the graph, you need to change bits and pieces. So that is basically interactive visualization. You can play with it, you can change color, apply anything. So that's when we use Jiffy. That's basically an alternative for NetworkX. Anyways, let me show this thing. I suggest you guys also open Google Colab along with me. I'll create a notebook, new notebook. Okay. Just a second. Okay, let us start. Import NetworkX as Linux. Just ping me if you have any doubts. I also want you to try this with me. It takes a time, a bit of time. Okay, how do we use it? And next dot, LDOS running graph. Let us see what output does it give directly. It gives, okay, so say we have 10 nodes. The probability is 0.5. It is giving a graph. Okay, so let us initialize this as ER1 print ER1. Graph with 10 nodes and 20 edges. It has even 20 edges, see. Okay, I'll run it again. 10 nodes and 22 edges. See, you guys getting it? The edges are changing every time you run it. The count is changing currently. I will show you how the edges are changing as well. Okay, getting it? Guys, say yes or no. Shikha? Okay. Everybody else, you are getting it? At least you can like from here. See, where's that reaction? You can just press like. I'll get to know. Okay, so let's go back to this notebook. Just a second. Hmm. So what happens is, why these edges are changing? Every time you run it, see. But how do we fix it? I don't want the output to change. What I do is I set seed is equals to say 1, 2, 3. For ER2, seed is 1, 2, 3. Print ER2. 10 nodes, 25 edges. Let's print it again. 10 nodes, 25 edges. Let's print it again. 10 nodes, 25 edges. It won't change because the seed has set a pseudo randomness so that it's fixed. I use seed 20. I use seed 20. Yes, we can use NetworkX has libraries. I will show you. Actually, I covered it in first, second class, but still I will show you. I'm just showing you how this seed is affecting the randomness. Okay, I will print all the graphs and you will see. Okay, so you don't have to remember everything. Just see, visualize network X graph. Go to drawing. Use this. Just a second. This is a very basic visualization. Okay, let me show you. I run it again. You might think actually we should. How do we name? Can we name? Basically, we cannot name. So the thing is, since these nodes, their positions are not same, so that's why you might not be able to tell whether the two graphs which are printed. See, last time one node was very far away, it had just one edge. Now they have at least two edge per graph. Okay, per node. Yeah, it's different because we are not setting the seed here. That is why it's different. Now we set the seed and print it. And this graph will every time it will be same. So this node has one edge, this has two edges. See, this will always be the same. See, two edges, one edge, same every time. Two edges, one edge. That is the best thing about seed. You can fix the randomness. To do it for three. What is three right now? One edge separately. Others are almost with at least three edges. Run it again. See, see. It's always the same graph. So seed basically prevents this randomness happening. Okay? Shikha, your doubt is cleared? We can fix the layout. Take some layout, say draw spectral. Okay? Let me draw spectral layout. So spectral layout on ER1. We draw ER1. So I fix the layout currently. See, this will change. This is changing irrespective of we run that function or not because this draw has randomness. But this will not change. This will always remain the same. See, I'm not running this thing. I'm not running this thing. Still, the layout is changing. See, the layout is changing, but here it won't change. Because spectral layout has particular setting to show the nodes. It follows it automatically sets a particular seed, and this all prints the same graph every time. But if I change it now, let's print it. How many nodes? This currently has 1022. Now it has 1023. It will change a bit. See, it changed. So that's how you fix layouts. Okay. No, 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 you don't have to give XY positions, and that's a bad practice to print the nodes and the graph. There are layouts which basically ask you to take the position and print them, but they're manual for manually drawing it, beautiful uh, representations of graphs. But that's not preferred. That's not preferred in case when we have large number of nodes. You cannot give positions to all nodes. Okay, you can do it, but it's not preferred. Basically, it takes a lot of time. So we discussed ER model. Okay, ring lattice. Shall we try ring lattice? This is the ring lattice, correct? Here's the notebook. What was ring lattice graph? Anybody? You guys have studied, right? What arguments does it take? Let me check. I'm just checking. Is it given? It takes NKP. NKP thing is given, right? Or not? It's not given. Is it given? Screen is not. How how are you guys? Now is it visible? Sorry, sorry. Yeah, did you guys get it? This thing. Vishal, this was visible, right? Okay, okay. Oh, okay, okay. Okay, okay. Sorry about that. So yeah, I don't think so. Then book it is given with NKP thing. The ring lattice thing is very basic. Basic in the sense they are just small dividing property, large dividing property, and these probability. These things are given. Okay. So, but it's not given in terms of that. Okay, let's visualize it. So it requires NKP. N is number of nodes. K is each node is connected to k nearest neighbors in K topology, and this probability of dividing each edge. So let me show you ring this graph. Spin is visible, right? Okay. This is the neighborhood. How many nodes it gets connected directly is the neighborhood. It's connecting to two nodes right now. Okay. This one is connected to 1, 2, 3, 4. This is connected to 1, 2, 3, 4. Okay. So this is K. This is the value of K, which decides how many nodes it gets connected to. Where's the notebook? So we take 10 nodes, we set K, sorry, we take say 10 nodes. We connect every node to 4 node with the probability of 0.5. Next dot, see it's giving graph again. Let's next dot draw. WS1. Worst visualization to visualize NX, but you see, each node has 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, because it's given probability 0.5, make it 0.9, 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 4. The visualization is not good. Let's visualize it in ring lattice format, whatever it is. So let's see what ring thing we have. We have shell, we have spring, we have spectral, we have circular. Let's print it circularly. Okay. Hmm. Circular layout for WS1. Let's draw WS1. See, it's almost similar to that thing. Let's increase number of nodes. Increase them to 20. Let me remove this. Okay, let it be like this. See, you seeing the structure? If I make the probability equal to 1, it will be more connected. So that is what knows. If my camera, open my camera, I will show the figure in the book. Circular layout. I'm using circular layout. What layout I'm using? I'm using circular layout. Yeah, sorry. Um, okay. See, p equal to 0, visible? P equal to 0, some intermediate p, then p equal to 1. For p equals to 1, these edges are going away. For random, some small p, the round edges are there. For p equal to 0, all edges are there, all circular edges. So let's do it. Let me show for p equal to 0. Wow, beautiful. Even this draw has automatically drawn it in a circular way because it is connected. See, how would I show you? See, 1, 2, 3, 4. These four edges are connected. So k nearest neighbors are are connected automatically. This thing, this thing, this thing is increased, moving the edge. This is increasing the probability of it getting connected to some other farther node. Getting my point? Vishal, getting my point? Vishal, you getting it right? So basically, this probability allows for the edge to move from k nearest neighbor to any other farther node. If I make this probability 0, only nearest neighbors are connected. This is the first nearest neighbor. There's the first nearest neighbor. There's the second nearest neighbor. This is the second nearest neighbor. It's not getting connected to fifth nearest neighbor. Okay. If I increase this probability to 0.1, sorry. Yeah. Yes. See, if I increase to 0.1, this randomness has made this graph random. Okay. See, a few edges moved from, see, this edge has moved from here to here. This edge has moved from here to here. Okay. So that is what K does in case of this graph. What's Strogat's graph? Getting it? That is, I suggest you guys do this stuff to learn more about the concepts because sometimes visualizing in mind is not good. I mean, it's good if you can, but it sometimes create confusion. So even giant components you can visualize here. So I want you to try, I'm typing it here, try visualizing giant components in random graph. Yes, the number of edges remain same. They just get rewired. That is a rewiring probability. That is literally the word. Uh, am I right? It's rewiring probability. Yeah, that is rewiring probability. So that is why they get rewired. The number of edges remain the same. Otherwise, it won't be ring lattice network. It will be some other network. It can become over the time that Redos Rini network if it's that random. Okay. So yeah, that's that. And now we have Barabasi Albert model. Let's try Barabasi Albert model network. Just a second. So what does Barabasi Albert model do? Preferential attachment to existing nodes with high degree. That's what it does, correct? Let me just close a few tabs. Iteratively one by one, yeah, but how does it grow? It does it prefer nodes with low degree or high degree? Because randomness is there. Randomness is there. But if it's random, then why is it not called random network that is temporally growing? Why is it called Barabasi Albert model? We already have a temporarily growing network, okay? Yes. Why high degree? Why not low degree nodes? Because that's how social network graphs grow. You will always, a new person joining Instagram has a high chance of following Virat Kohli than it has a chance of following me. Yes, Virat Kohli is getting richer because he already has 240 million or whatever million followers. But me having 30 followers, I won't get 31st follower easily compared to how Virat Kohli might get 5,000 followers a day. So that number is very big. 1 plus 1 compared to 5,000 because he already has 30 compared to 50 million or 80 million followers. Okay. So I have a degree of 30 on Instagram. Virat Kohli has a degree of 50 million. So that's how it works. Rich gets richer. Why is it getting richer? Because the previous connections has made him popular on the network. So everybody wants to get connected to that person. So that is why rich gets richer. It's not like somebody is basically churning money out of you. It is we are giving the money to them. We are preferring them to get attached. It's like that. So yeah, what thing it requires? It requires n nodes. A graph of n nodes is grown by attaching new nodes, each with m edges that are preferentially attached to. Okay, so let's take n nodes and say we want some five edges. Okay, 10 nodes with five edges. Nx dot nx dot draw. Sorry. See, whatever I do, number of edges is not changing because it is fixed by us. The number of edges to attach from new node to existing nodes is fixed by us. Okay, so number of edges won't change. It's just how the rewiring is getting done that is changing. Let's print the graphs. Uh, Let me draw it in spectral layout. In that way, the layout will remain same for all the graphs. Spectral layout. Then I also show the seed thing. Okay, let's draw it. Nice. Let's not use spectral layout. Let's use planar layout. That's the problem with spectral layout. It basically converts it to something like star network. Okay, G is not planar. What layout shall we use? Circular layout. Let's try circular layout. Easier visualization compared to run it again. See, the graph is different. Let me minimize it. The graph is different, but you will notice one thing here. Even that's not the same. Okay. Okay, so what it does, it introduces first node, then it introduces second node. With some probability, it is introducing edge. So at then it introduces another third node. Okay, so gets what can we see here? This node was introduced first. Say then this node was introduced second. Let's assume that condition. Then the third node came, which we cannot see here because we have not passed an initial graph here. If we had passed initial graph, we can see. Okay, see if none, it starts from n from a graph, star graph on m plus 1 nodes. Okay, so we gave it 5 edges. It will start with 6 edges. See, so you can see 1, 2, 3, 4, 5, 6. These edges will have very high degree because it was created in the in start, or say these edges were in start. So something like that. It came, then it started attaching remaining nodes. Say 6 edges, 6 nodes were initially present. Then it put another 4 nodes, and then preferential attachment started on it. Okay, so that is how we cannot know basically what sort of what node was starting node until we draw, say we pass into some graph into it. Okay, so you can pass. Okay, forget it. Uh, Let me create a small Barabasi Albert model with 4 nodes and 5 edges. It is in BA1. Okay, just remember it. Error is the nodes cannot be less than edges. So let's make it 6 because it has to initialize with some m plus 1 nodes. And if the nodes are not there, see. So this is basically the starting. So if I put 6 nodes, 5 edges, so it will create a basic model with 6 nodes only, and this will be the attachment. So see, the initial attachment looks like this. The 6 nodes get attached to one node like this in spectral layout format because that is the only possible thing which Barabasi Albert model can do. It can create a node with higher degree, and that once that higher degree node is created, it will start putting uh, the other nodes in that node itself. Okay, if I change it to say 7, then you will see some extra edge. Then this see these extra edges have come for this node 7. Okay, so this node 7 came up in the picture. Apart from that, these nodes were starting nodes, And we have given the condition it should connect to five edges. So one, two, three, four, five. It's connecting it to five edges. Okay, so let's use BA1. So we pass 10 comma 5 comma BA1 and let's print it. 7 nodes and 10 edges cannot be used to generate. Okay, we cannot pass a spectral model in it. Hmm, let's use ER3. We need high nodes and low edges, something like that. So what's happening? WS1 we can try. See the problem. This thing is very interesting. WS1 with two edges and zero, it's like a ring, proper ring. Okay. Hmm. Let's do it with something higher. It cannot be performed. 50 nodes and 9 edges. It looks like this. Let's use BA1. It's not working. Copy of initial graph is used. It should be a connected graph for most of the cases. We tried, it didn't work. Can we use this thing? 2 comma 1 thing. Let's try 2 comma 1 thing. Hmm. Let's try it on this. Annex dot. Acha, it should be add edge. Let's pass this G. What's happening? See, the main problem is to randomly generate a subset of M nodes where each node has desired probability. The neat way is to map the list of weights. What is a star graph? Let's create a star graph. What is the probability of star graph? Uh, add edge 1 comma 2, add edge 1 comma 3, add edge 1 comma 4, add edge 1 comma 5. Now this should work. Okay, it's not working. Single node, if I try to pass single node, okay, let me try a single node. What's the use then? Add node 1. I think we need to pass something. What is G? G should be classes graph. Class is correct. Okay, leave it. Let's not waste time. What I'll do is I'll figure this out and we can discuss how to pass initial graph in Albert Barabasi graph thing. Okay. Till now we can just simply see. So we saw how Albert Barabasi model says 7,6. So initially it will create a graph using six. Sorry, something happened. Am I audible? I think I am. Hello. Cool. Okay. Hmm. So what happens is it creates a graph with k plus 1. So that is 7 nodes initial graph. So it looks like this. But if we pass 8th node, then 8th node will become the node for preferential attachment. It gets attached to almost every node randomly, except leaving this because if I make it 7, then again it will be a network, so something like this. So the issue with this kind of thing is we cannot create another node 9 and we cannot connect it to every other node. It will always leave out one node because otherwise this initial condition is violated and this star graph is not created. Anyways, see, the left out node is always this one with degree 1, not this one. You do however you want. You will this node, this extra node will always leave out this node. Sorry, will always leave out the node with least degree, not with higher degree. Okay, so that's how Barabasi Albert model works. Yeah, that's all about visualizations. Any other thing you want to discuss? We don't have time to discuss a new concept. So any basic thing, how to use Jeffy, how to use blah 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 stuff. Vishal, anything you want me to discuss? Okay. So what shall we do? Shikha? Priyadarshini, you want to ask anything? Any doubt basic? No, okay. Anyone else? Listen, just four, five people are completely silent. Hmm. Okay. We can do. That is the whole point. So there are synthetic data sets available. Huh? What I want to do is try this thing out. Okay. Search for Snap Standard. You will, sorry, Stanford. You will get Stanford Network Analysis Project. So what you are saying is, nah, Twitter data, blah blah blah. That's all. Basically, what these companies do is they also want some like people like us, open source people, to perform link prediction, create new algorithms. So they release their data sets, but that data that data does not contain names. Okay, what it does is they make it pseudonames. Pseudonames basically say you are Vishal, they will replace you with Alex. Yeah. So say Twitter data is almost already there. Twitter and meme tracker, you go here, Twitter 7, it has high number of nodes, high number of tweets, URLs, hashtags, everything is there. Okay. As per request from Twitter, the data is no longer available. Elon Musk. My PhD topic. I basically work in graphs only. I work in graph generation, not using Barabasi Albert model, of course. I work on graph expansion using deep learning, GNNs, this stuff. Then I also work on recommendation systems. How to use these graphs, not normal data, not metadata of item, how to use these knowledge graphs, hierarchical graphs to generate recommendations for users. Session-based recommendations means temporally improving like that. So that is what I work on. That's all. Like this is a very basic topic. I just completed my first year. I'm in second year. So over the years, the complexities will increase. Then I can discuss more about it. Currently, I don't have a lot of idea how to do a lot of things. So that's what I'm learning. No, no. Okay, don't. I just want to tell you one thing. Don't think GNNs are very big thing. Okay, they are just weighted aggregations. Weighted aggregations means, let me show you. You want to find the embedding of this node. What you do is you find the embedding of this node, you find the embedding of this node, you find the embedding of this node, you find the embedding of this node. They are just neighbors of this. Okay, direct neighbors. Then what you do is you do a weighted average. Then what you can do is you find you if you use say in machine learning you use layers now. So if you create another layer, then you can also get the embedding of this from here we go here, then we go here. Then from here we go here, we go here. From here we go here, we go here. So that is what we do. Yeah, so basically increasing the layers in GNN, it increases the neighbors into consideration for creating the embedding. So that's what it, yeah, please, please. Very basic thing is you can take the edges from knowledge graph. Okay. If the edge is connected, you consider it one. then take some random negative samples which are not connected at all. Just a second, I will explain it to Shika. Okay, so take positive samples which are connected, take out one by one edge, then take out negative samples which are not connected. Then you can take embeddings using natural language processing methods, or say using metadata, and you can train a GNN, you can train BERT model, you can train anything using that. That is the basic thing, how you do it with graph neural network. Oh, sorry, how you do it with knowledge graphs. Very, very basic thing. I can on Kaggle, if you go see knowledge graph classification. See, um, open this tutorial. What is knowledge graph? Node A, node B relationship. They are taking something, they are doing something. What ultimately they'll do is they will create knowledge graph. They will use this edge for training positive sample and this negative edge for training negative sample, and they will train a model. Okay, they will predict. So what it does it basically converges. Say, it takes a neural network. It will ultimately be a soft sigmoid function. So what sigmoid function is doing? It is trying to learn zero and ones between. So when the edge is connected, sigmoid function makes it closer to 1. When the edge is not connected, it makes it closer to 0. So when a new node comes up, if it's connecting, the probability will be high. Sigmoid will be 0.99 something. If it's not connecting, the probability will be low. That is how the inference part is done. Very basic thing. No, no, no. That is empirically thing is very wrong. Coming to Shikha's question, is it possible to add JNN layers to a point where all embeddings are same or similar? There is a case, okay, when the embeddings are similar. So how does it happen? So say you take a ego graph, okay? Ego graph has one link for every node, and you take one GNN layer, it will learn the embedding of ego node from all the surrounding nodes. But when you take two GNN layers, okay, so when the GNN layers are increasing higher, it's a general convention, okay, when the GNN layers are higher than the number of, uh, say the diameter of the graph. So diameter of, basically the number of edges, sorry, GNN layers are equal to or greater than the diameter of the graph. So the diameter of ego network is 2. From one node to another node, you can go in 2 hops. Okay. So when the diameter, sorry, the number of layers is higher than the diameter, in that case, the embeddings flatten out, smoothen out. So that is known as graph smoothing. That is a very big problem, and that's the thing researchers work upon by, introducing random noise in the nodes, the noise based on the embedding, the noise based on distribution, the noise based on number of neighbors, something like that. So they keep on adding noise to GNN layers in between on the to nodes embeddings. So that's how they avoid smoothing out of edges or smoothing out of embeddings. That's how it is done. It is like your question. You read it somewhere that empirically 4 5 is a good. That is true because generally in social networks we do not have communities when the diameter is very that much big, 4 5 6, something like that. If you take a fully connected graph, something, so in that case, fully connected graph with say 20 nodes. So how many edges will it have? It will have a lot of edges. 20 into 19 by 2, that is 1800 something. Not 18, sorry. 380 edges. 380 edges. So what will be the diameter? The diameter, say, the largest possible length. The largest possible length will be from one node there to there. So it looks like you might think the edges from one node to another node maybe 20 something, 19 or something like that. but so it can contain it can be trained using 10 layers of GNN, but it's not true with the fourth, fifth layer, the sixth layer. It starts smoothing out because you're not just taking one path, you're taking all the paths, and ultimately these paths stagnate the embedding at one level. It's not getting smooth and it's stuck. So you have to basically reduce the training more, but reduce the loss more in order to make the embeddings different. So that's how the noise introduction part is used. Then basically the other types of GNNs are used and not in Euclidean space. They are used in, say, hyperbolic plane or somewhere. So that's how you can learn embeddings based on the position. Say you take a node with high degree and you place it near the tip of hyperbola, and the low degree nodes are apart away from that hyperbola. So you introduce the hyperbolic noise based on the number of degrees to the layers of GNN. That's how you improve the learning part. Very basic stuff. If you start using literature, if you start doing literature on graph smoothing techniques or avoiding graph smoothing, you'll get to know very basic stuff. Okay. So yeah, yeah, it's an interesting topic. It sounds interesting when you once you start doing it, it's very frustrating. Let me show you one thing. Okay, let's go to Scholar. Hmm, graph. Smooth. See this Nurep's paper of 2022. It does that thing. It performs smoothing of embedding. Okay, over smoothing. Why is it happening? Okay, so it shows here mean aggregation for both subfigures. You just study this paper. Okay. It will take time. It won't, you can't finish this paper in one night. I'm attaching it here. So yeah, these are the basics of GNN stuff. Any other questions, Vishal? Any random question, anything about research, anything about graphs? In NLP, it's LLM. First of all, NLP, I should not say that, but the research, the applied research in NLP, now it has stagnated around LLMs only. Okay, you change the prompt, you fine tune it, you publish the results, you tweak the results. That's what is happening. Tweak the prompt a bit, present some new prompting strategy, and that's how you can publish the paper. In NLP, it's that simple. In graphs, LLMs have also come into picture, so you can basically feed the graph in a prompt. Okay, say this edge is this edge is this. What what are the chances this edge get connected? So that's how you can do in graphs as well. So NLP plus LLMs, these two things work like this. Most of the work is around LLMs only right now. Okay, figure it out yourself. I think like you might know better what you have hold on. So any other question, Shika? You can ask any other question like if you want. Right? Like, anyways, I cannot teach anything in 10-15 minutes. Any doubts on assignment? Any doubts like anything? Coursework, how NPTEL videos, anything? Shika, any doubt? They can be. That's what multimodal graph analysis is for. Metadata generally is of text format. Okay. So you have embedding, text embedding of a graph that you can get using BERT, you can get using, say, any other encoded model. Image embeddings you can get using ImageNet, sorry, ImageNet is data set, that like ResNet or something, pre-trained internet, pre-trained network, you can use anything. And then you can concatenate these two embeddings, you can pass in GNN, you can update these embeddings. A lot of things you can do. Edges indicate captions. Even you can use hypergraphs. So in hypergraphs, the edge exists between multiple nodes. So that edge embedding can also be trained for different nodes. So for node A and B, the embedding is different. For node A and C, the embedding is different, but the edge is same. Not so edge is same, but embedding will be, how should I say? So you're getting the point, right? Training is not basically training. You're training now. What you're doing is you're learning if the edge is present or not. Okay, so you're training the embeddings of nodes. You're passing a node. You're checking if the edge exists or not. So, but it's basically link prediction problem. Link prediction problem, what it does, it checks whether the edge exists between two nodes. It gives out that connection with some probability, and that is trained using sigmoid function. So you have to basically train a sigmoid function based classifier so that it gives you the edge, not embedding the edge, predict edge relationship or not. The edge relationship between two nodes. So that is not edge embedding per se. That is basically what, say in knowledge graph you have H R T, head, relation, tail. So that relation you have to learn the embedding. That head and tail can be different. They are very different. But relations are constant in a knowledge graph. They're not constant per se, but they are not very variety. There are not a lot of varieties there. A resides at B. B can be a location, A can be a human, but resides will exist multiple times. So that is what we have to learn. Okay, using link prediction thing. So each you have to train model. You say you have five edges, five types of edges in a knowledge graph. So what you can do is you can train five different models, first of all, to predict if that type of edge exists or not. You can take majority voting, you can choose the highest rated edge, and that will be present between two nodes. This is one way. Other ways are non-neural network based, so they are there as well. Any other doubt? Vishal, downloading videos. What videos? Okay. What videos are you trying to download? Lecture videos. Screen is visible. Let me show. How are you downloading it? Is there an option to download? Let me check. Oh, this thing. Go to, you're following it, right? I'm showing. Click download. Not downloading. Hmm. What you can do is, I know, yeah, I saw it. Just a second, see. You can download it from YouTube. Some extension SS. 50 or something like that. I don't know. You can download from here. See, it downloaded. That's how you can download. Basic setup. Okay, any other doubts? Vishal, anything else you want to discuss? 5 more minutes. We are here. Uh, Next time, naga, you guys at least study from book from wherever you want. Like if you have Kindle, you can purchase Kindle. Anything. Just study. Okay. The thing is, from videos, you don't get a lot of stuff. You need to sit at home. You need to study whatever's taught. Yeah, no problem. So that way, na, once you start learning the concepts, you see you'll come to know what how much you don't know. Okay, because you I showed you, yeah, this is the stuff, these are the equations, but once you study those equations, you come to know, yeah, how is it coming? You go back, you see, so you start connecting the stuff. So that's what I'm saying. Just study on your own. You will of course you will get some doubts. It's not an easy subject till week 3 and week 4. I don't think so. It's easy when you guys are doing it. So later in the course, it's going to be difficult. Community detection part, it's very difficult. Then cascade behavior, cascading. Later in the course, a lot of theoretical stuff will come, but it will start becoming difficult. So yeah, that's something. Just start studying from now onward, so that later on you won't face difficulties. Now we are today is fourth week, right? We have 8 more weeks, 8 more chapters, and out of 8 chapters, I can certainly tell you 5 to 6 chapters will be very difficult. If you want, if you just don't want to pass the exam, because exams are easy, assignments are easy. But if you want to uh, learn the stuff, then I suggest you start studying. Social network analysis. I will share the link here. You can just buy Kindle version. I don't think so. 100 rupees makes a difference. You just buy hard copy. I'm sharing it here. This book is very good. Like if you are studying social network, you should follow this book. Barabasi, those books, they are very specific to the algorithm they have implemented. But this stuff is good. In chapter in week 4, when you will start link analysis, uh, what is week 4? Yeah, it is link analysis only. Sign graph. So that is week 4 is very important. That's why just I showed you link analysis. Why links are important. Why strong ties, bridge, page rank. These numbers are important. Then we have week 5. Week 5 is already live. You will see community structure, lower and community link partition, this stuff. Okay. Then week 6 is link prediction. In week 6, you will study train test split. Week 6 is easy. Week 6 is easy in scenario like it's very basic to machine learning. Week 7 is cascade models. Cascading is going to be not difficult. The theory is there's a lot of theory in cascading. So you have to mug up order to understand. So you can only understand if you start reading stuff because in lectures you can get only so much. Then we have epidemic models. And what do we have in next chapter? Anomaly detection. Yeah, anomaly detection is. I don't think so. It is that difficult. But then last chapter we have graph representation learning. Chapter 9, 10. This stuff. Later it becomes easier. The community detection chapter is a bit difficult. Not difficult per se, it's not easy to understand in one video and one lecture because there are a lot of algorithms of community detection. They follow different strategies. There are a lot of conditions of for those algorithms. So they literally have written algorithm step by step how to do it. So I would suggest start reading. At least you can videos are already available in internet. You can just make a list of topics which are being taught. You can start using Wikipedia to read more about them. Wikipedia already has a lot of content about this stuff, and this is Wikipedia explains this very well. Okay, so you can read that, and yeah, then you can just get your doubts cleared. Because if you don't have any doubts, this means you have not studied anything or you have studied everything, and that's not the case. Second one is not the case. So just study uh, from just read out this stuff because video lectures like Shikha had a doubt how that equation is coming. That is very simple. But if you read in the book, you will find a lot of other stuff. Why is it there? So the equations are marked. You have to go back. You have to study like that. Okay, that's that. I think that will be all. Anything else you want to discuss? I have to upload it. So I just copying. I think that will be all then. Um, any doubts till now? For 2 3 minutes we are here. You guys want to discuss anything else? Sure, Shika, thanks a lot. Yeah. Okay then. Bye bye guys. You can drop the call. Thanks a lot. Good night.